Hey everybody, today I just wanted to do a kind of crash course on DAQmx in LabVIEW. So I just want to talk kind of high level what this API looks like, typically how you're going to be using this, and then walk through some examples, and then I'll be doing some more in-depth videos on different types of measurements and different kind of specific scenarios of DAQmx. So first off, just want to show where you can find the DAQmx functions in LabVIEW. So if you open your functions palette and go to measurement IO and NI-DAQmx, that's where you're going to find all of the different DAQmx functions. So you're able to use these with a ton of the different NI hardware. So there are different USB type DAQs that support DAQmx. You can use them with CDAQ devices. So you can buy like a CDAQ chassis and insert the C series modules in. Certain compact Rio devices support DAQmx. Field DAQ, a whole bunch of different NI hardware. So very versatile. The API is actually really well put together. It's super simple to use, and you can use it for something simple like reading a temperature every few seconds to really high speed IO type things. So like I said, this is the palettes. You can find kind of this, there's this home page, and then there's kind of some more specific things down throughout here. There is also, I wanted to highlight the DAQ Assistant. So I'm not actually going to talk about the DAQ Assistant right this second. I'm going to do a separate video on that. But the DAQ Assistant, what it is it's an Express VI that's basically going to pop up a little window when you drop it down and allow you to configure some things. So that allows you to be able to basically from a GUI click, hey, I want analog input on these channels and I want to read it at this frequency, and then it's just going to go and basically script up some code in the background for you that does that and allows you to create that task super simply. It's actually really easy to use, and then if you want to, you can convert that to actual DAQmx API code as well. So I'm going to do a separate video on that. For this I mostly just wanted to focus on the actual DAQmx API. So like I said, we kind of have these functions up here. These are your common DAQmx functions. So these are the ones that you're going to be using most of the time. And there are a ton of other things throughout the advanced that are used rarely. But these ones, if you understand them, this is going to serve you for just about everything that you need to do. And there's kind of just special scenarios where you need to venture off into some other stuff. So first, let's look at this DAQmx create virtual channel. So if you drop that down, you can see that this VI is polymorphic. So you're going to use this, doesn't matter what type of measurement you're taking or if you're generating a signal, whatever it is, create channel is kind of your starting point. So you're going to actually here define what it is that this DAQmx task is doing. So I think the easiest way to start out is looking at analog input. So you can see here it breaks down a whole bunch of different types of analog inputs. So there could be something like a voltage, temperature, current, and then there's a whole bunch of different kind of more specific types of analog inputs. So depending on the type of measurement that you need to take, you just need to select the corresponding analog input. So I'm just going to do analog input voltage for now. The next thing that we're going to want to mess with is this physical channels. So I'm just going to create a constant here. It doesn't have to be a constant. It could be a control. It could be a string that you load in from a file, all sorts of stuff. But let's just use a constant for now. So if I click on this, it's actually able to go and search for compatible modules and channels for the type of measurement that I've selected. So because I've selected analog input voltage, I get basically the IO that I have available that supports analog input. So for this example, let's select this. So you can see that this is CDAQ 6, which if you ever need to see, you can just open NI-Max. You can see I just have this simulated DAQ here, but you can see the chassis and you can see the cards that I have in the chassis. So basically this name here is going to be the chassis. I can customize that and I can name it something else if I want to. And then mod 1, 2, and 3 corresponds to the specific cards. And then again, if I want to, I can actually rename those as well in NI-MAX. So I've selected a channel now. So I've created my virtual task and I've selected a channel. Now, if I wanted to select multiple channels, I also can just add a colon right after that and then basically put the number that I want. So now I'm reading from channel 0 to channel 5. I can do that with as many channels as I want. Another thing that you can do as well is add other virtual channels to your task. So let's say I've got my voltage here. I want to read 1 voltage, but then let's say I also want to read a temperature from a thermocouple. So I can tie that into my DAQ task, and I can specify the channel for my thermocouple. So let's do that. So yeah, now I've got a task defined that is going to read voltage and temperature. And you could go on and on and on. You can tie in as many things as you want into that task. And yeah, also want to highlight, based off of the polymorphic instance of this DAQmx create channel, you're going to get different options on this VI. So I have here this maximum value and minimum value. So let's say the maximum I'm ever going to read is 5 volts, and the minimum that I'm going to read is -5 volts. So on this card specifically, I have simulated an NI-9205. That card has multiple ADCs in it. So based off of the range that I give it here, it's going to pick an ADC to give me the best resolution across that range that I've selected. So it's important that I input good values here, because that's going to actually affect the ADC that's used. So for example, if I do 5 to -5, and let's say the card you're using has a 5 to -5 ADC, and then suddenly your signal goes to 8 volts, well, it's going to be maxed out on the ADC, and you're only going to see up to the max voltage that the ADC can measure. So here you can specify that, and then it's going to try to optimize for the measurement that you're taking. They are optional fields, so if you don't want to write anything, or if your device isn't going to change anything based off of that, you can just leave it unwired. You also can assign a name to this, so you can add a custom name to basically, to correlate a name to this channel. You can also specify units. So for temperature, something like that, it's a little bit more valuable. For something like volts, your option is volts, or you can use custom units from a custom scale. If you notice down here, there's this custom scale. You can basically define a custom scale. I've talked about scaling in a previous video, so I really don't want to highlight that here. If you're interested in how you can apply scaling, I've created a video on that. Just look for it in the channel. I'm going to put together a DAQmx playlist that it'll be part of. You can apply a scale for something like voltage. That would be the only time where you don't want to use volts. So once we've created a channel or channels, depending on how much data we want across either a single card or multiple cards, we then can move on to configuring the rest of our task. So the most common next step is to add this DAQmx timing function. So here we can specify the timing of our task. Now for a task that doesn't require timing, like maybe you just want to write like a digital line high, you're going to create a task, write a digital line, and then destroy the task. You don't really need to define the sample clock, but for something like analog input where we're doing data acquisition, we'll want to define that timing. So if you notice here, we've got a few different options. So this first one I want to show is the sample mode. So our options are finite samples, continuous samples, and hardware timed single point. So finite samples is basically we're going to read a fixed amount of data. So we're going to specify the rate at which we read data, and we're only going to read so many samples. So let's say, we're reading data at 1 kilohertz, so 1,000 times per second, and we want 5,000 samples, which means we'll pull 5 seconds worth of data. So that's helpful when you just want to basically get a snapshot of data. I find that I use that not all that often. Most of my applications have used this continuous samples, which is basically I want to continuously read data until the task is stopped. So my software is going to start reading data over and over again until the software actually stops it. So this is what I most commonly use. I have used finite samples, but this is the most typical example for what I've done. And then there also is this hardware time single point. So this is basically a way to get single point data. I've mostly used this on CRIO, where I can synchronize to the CRIO clock and I get good timing and I still get single point data, which I'll do a separate video on that. I don't really want to talk about that here. In most use cases on like a Windows computer or something like that, we're using finite samples or continuous samples. So I'm going to use continuous samples for this example. We also have a few other fields here. So we have the rate. So I can specify the rate at which I want to read data, and this is in units of hertz. So default is 1000 hertz or 1 kilohertz, which means I'm going to get 1000 samples per second. If I don't want it that fast, I can change it to whatever I want, as long as it's within the bounds that the device you're using actually supports. So you'll have to look at the data sheet of your specific DAQ hardware and determine if your device can support the speeds that you need. If not, there's some devices that can go incredibly fast, and some of the kind of lower cost hardware, some of the USB hardware can be a little less performant. So if you get like a USB 6000, they're really cheap and they're actually pretty nice DAQ devices, but your ability to sample at high speeds is really low. So yeah, big difference in terms of what you can get with different equipment. So you'll want to shop around a little bit and just find what hardware meets your needs. You also can specify the source of your timing, which in most situations, at least in what I've done on like a Windows computer, I haven't needed to use this at all. But you are able to specify basically a specific clock. So on my CDAQ, you can see I have a 20 megahertz time base, an 80 megahertz time base, and I can use all sorts of different clocks. I can even use like PFI lines. I found that mostly just useful in very niche situations, so I don't really want to focus on that here. I'll do a future video on that. Yeah, and then there also is this samples per channel. So this is another optional field. But basically this allows us to, well, I guess before using that, right, once I specify my sample rate, LabVIEW is basically going to determine a buffer size for me. So this way, LabVIEW is communicating with the DAQ hardware, and Windows especially, right, is not super reliable timing-wise. I mean, to a certain point, right? Like, if you're wanting to read data every millisecond, well, you're not really going to get every millisecond. There's going to be some jitter in there, and so buffering handles that for you, right? So let's say your software freezes up for a second, right? Well, the DAQ's still running and you don't want to miss data. So the DAQ is able to buffer data and then transmit it over to the device. So when you specify your rate, LabVIEW is automatically going to determine an appropriate buffer size for you. Now, the samples per channel basically allows you to specify more, kind of a specific value as well. In a lot of cases, you don't really need it. As long as you're reading data at a good frequency, and I'll talk about what a good frequency oftentimes looks like, you shouldn't really ever have to mess with that. There are, again, certain niche situations where you can. In this video, I just want to highlight kind of what you need most of the time, and then we can do future spin-offs onto different avenues of DAQmx that are a little less commonly used. So now I've specified my timing. If you notice, this one is also polymorphic. Most of the time you're going to be using this sample clock. There are special situations where you'll want to use different clocks, different ways to set your timing. Sorry, I shouldn't say clocks, but different ways to define the timing. But almost all the time you're going to be using sample clock. So this is what I'm going to focus on here. So now that we've defined our timing, we've created our channel, defined our timing, now we can start our task. So there is this trigger function, and I'm going to do a separate video on triggering as well, but just wanted to highlight triggering you would also add before starting a task. So trigger is basically a way, if you've ever used like an oscilloscope, right? You define some sort of thing to basically trigger your acquisition. So you get like a one shot, on your O-scope. So I could say like, hey, trigger on a rising edge, and I want that trigger level to be maybe 5 volts, right? And then once it detects a signal on that channel that hits 5 volts and it's rising, it's going to basically acquire however much data fits onto the oscilloscope screen and then display that for you. So triggers here in DAQmx work very similar. So I can do start triggers, where I can basically start this acquisition once it detects like an edge, and that could be digital or analog. I can make it start at like a specific time, etc. So I can also use reference triggers, which we're going to talk about all of these in a separate video. Just wanted to highlight that they exist. In this video, I'm actually not going to use any triggering. But yeah, think of like an oscilloscope, right? You don't actually want continuous data. You want to capture data once a certain event has occurred, and that's what triggers are for. So next, we're just going to use this start function, and that's going to start our data acquisition task. So before this, the DAQ hardware is not actually running. We're just basically defining how it's going to run. So now we can actually start reading our data. So I'm going to grab this DAQmx read function. And if we were doing some sort of analog output task or a digital output or a counter output, we would just be using this DAQmx write instead in place of where this read is. And I'm going to do videos, like I said, on all of the different types. So if you want to know, hey, how do I do a digital output or a counter output or something like that, those are on the way as well. So yeah, we've got our analog read here. I'm going to wire that up. And I'm going to put this inside of a while loop because I want to continuously read data. We did configure our task for continuous data, so I want to be able to continuously read data until I tell it to stop. Now, on our DAQmx read, we've got, you'll notice first of all that this is polymorphic as well. So I can read all sorts of different types of data. Digital counter, power. In our case, right, we've configured an analog input. So I'm going to want to use the analog option. And then we have a few options. So I can read either a single channel, multiple channels, or unscaled. So if you remember from our DAQmx create virtual channel, we are only reading a single channel. So I want to read just a single channel. So if I go to single channel, I basically get the option of either single sample or multiple samples. So basically every time I call this DAQmx read, I have the option of either pulling back a single sample or I can read multiple samples. So so in our example, right, we're reading data at 10 hertz. So that's 10 samples per second. So if I want to read data, one data point every 10th of a second, I could do single sample, single channel, and I would get that. But if maybe I only want to read data twice a second, I could do single channel, multiple samples, and then read chunks of data. So it's really up to you on what you're trying to do. In this case, I'm going to read multiple samples. So let's do multiple samples 1D dBl. And if you notice, it supports different data types. So I have options here of a 1D array of voltage values, or I can use waveforms. And same thing goes for single sample. I can either read a single scalar value, or I can have that output as a waveform. So it's totally up to you in terms of how you want that data received. So yeah, for this example, I'm just going to do this. Now, if you notice, there's a couple of inputs here. So first off, I have a number of samples per channel. So I'm here able to specify how many samples I want to read. Which in my case, I just want to read data twice a second, right? So we're sampling at 10 hertz. I want to read data twice a second, so I'm going to read 5 samples at a time. And now the cool thing about this is the DAQmx function is actually able to wait until 5 samples are in the buffer, and then it's going to return that data. So I don't need to specify in my loop some sort of delay or something like that. The DAQmx function will be my delay. And then there's also a timeout, so I can specify how long this is going to wait for that sample before this thing throws an error and just moves on. So you don't want it to just wait forever because maybe that data never comes. So yeah, here we're able to specify that timeout, which by default is 10 seconds. But so if you wanted to specify a different value, you can. And then let's wire that across. Sweet. And yeah, there's that. So now we've kind of got this set up. And it's just basically going to read data over and over and over again. Once we're done, there's 2 other functions to look at. So we've got this stop and we've got this clear. So stop, what it's going to do is basically just going to stop the measurement or generation. So just like the name suggests, we're going to stop that task from running. So there's different scenarios. If you notice, clear, if you read the description, this says this clears the task. So this is basically going to stop the task and clear it out entirely. The stop just stops the task. So from a stop, I could actually go back and restart the task if I wanted to. From a clear, the task is done. So I would have to go back through my code and basically make that, recreate the virtual channels, define timing, and start the task. So in some scenarios, you'll want to be able to maybe start and stop on the fly. But clear is kind of like your final, I'm done with this task, it's done. So I could just drop the clear here and wire that up, and that would work just fine. It's going to stop the task and clear it out entirely. You'll see a lot of code that does this, and this is totally valid as well, where we're just stopping the task first, and then we are clearing the task. Functionally, those are doing the same thing. So here's our really simple example. So if you notice, we've used just about all of the functions that I said were the high frequency functions. So we've created a channel, we defined the timing, we talked about triggering. I'm not actually using triggering in this example, but there's going to be a future video on triggering. We started our task. We're using the read function, which the write function works exactly the same, and I'll be highlighting that shortly. We're using the stop function, and we're using the clear function. So the only function we didn't show here is this wait until done. So this is basically a way to basically halt your LabVIEW code from executing until either a measurement or a generation, like an output, is done executing. So this is really helpful if I maybe want to generate like a square wave, for example, and I want to generate a specific amount of pulses. Well, I can tell it to generate that, and then I can just drop this wait function there, and it's able to wait until that generation is all done before it closes out the task. That way I don't stop the generation from stopping prematurely. So as we start getting in, I've mostly used this in output task, although it can be used in analog inputs. So if I defined, hey, read a finite samples, I could use like this for making sure that I get that amount of samples. But I've mostly used it for outputs, and I'll be talking about that in a future video. So yeah, there we've got our simple task. Now let's just go ahead and drop a chart here so we can see our data. And yeah, let's put that into our loop, and then we can run our simple DAQmx example. Sweet. So let's run this. And you can see we're getting data twice per second, and we're getting chunks of 5 samples every time that we get that data. And it's able to just run continuously over and over again until eventually I click stop, and it stops my task. I can go back again and run this, and over and over and over again. So yeah, that is kind of your DAQmx fundamentals. So really, as long as you understand these functions, that's going to work super well for 90% of your DAQmx applications. There is just a little bit more to DAQmx. I mean, there's quite a bit more in here, and we're going to go into detail in a lot of these other things. So stay tuned if you're interested in DAQmx. I'm going to be talking about next how we can do some basic write functions, triggering. We'll talk a little bit about these different nodes, and then we're going to go through some different measurement types. So, right, like what are the options I can use when I'm reading temperature? What are my options when I'm generating like an analog output waveform or pulses or something like that? So we're going to talk about all of those things, as well as we'll deep dive into some of these advanced functions. There's some config functions that we'll talk about and whatnot. So if you're interested in DAQmx, learning a little bit more, stay tuned. There's more to come, and thanks for watching.
Canon Controls is your gateway to mastering LabVIEW. Dive into programming for data acquisition, industrial communications, and manufacturing automation. Explore how to enhance your projects with cybersecurity best practices. Join the journey to elevate your skills and secure your systems with every episode.